Okay, cool guys. So today we'll be studying square root decomposition. Before I start this, just a disclaimer that I did have a surgery and I haven't, fully recovered. So I might fumble a bit. Please bear with me. Okay, so what is square root decomposition and where is it used? So the first point is that it's used for range queries. And if you had rendered the previous lecture that was on segment trees and lazy segment trees, you'll know that range queries could be like anything, literally anything. You can get me the sum of LR, or you can get me the max, min, XOR, whatever for LR. But the additional operation is the update operation. And I'm specifically saying that I want to update a particular point, so I can say that okay, one kind of a operation that I want you to do for me is that get me the sum in the range L to R, or let's talk of some numbers, maybe in the range 5 to 10. So you will be having an array. So get me the sum of the elements which start at the index 5 and end at the index 10, right? So you get me this. And the set of operation could be that update the element at point maybe like 7, right? So these are the two kind of operations. Now let's try to understand what would be the worst case complexity. So in the worst case, you can say that okay, I'm just gonna use array, right? And whenever you say that okay, get me the sum in the range L to R, I'm just gonna traverse and I'm gonna like sum up all the elements in the range L to R. Now since your L to R can be of the order of n or of the order of the entire array, right? Hence the complexity of a single query becomes order of n, right? Let's say there are q queries in total, so that overall time complexity becomes order of q into n, right? This is a bad algorithm. What if we want to reduce it? Maybe like reduce it to something like order of q root n. Then what we can do? At such places, you can always use square root decomposition. Now let's try to understand how does this even work. Now the very basic or foundation of it is the simple fact that a root n multiplied by a root n would give you n, right? A very basic concept of mathematics, doesn't need any justification. So root n into root n is equal to n. Now the way we are going to use it is we are going to say that okay, this is the entire array we are having, right? So this is our entire array, and on this, let's say this has a length n. I'm gonna divide it into pockets of length root n, right? So I'm gonna say that okay, this is the first bucket, and this would have elements from 0 to root n minus 1, right? Since zero based indexing, or you can say from 1 to n, 1 to root n. But since we are gonna talk of zero based indexing, so I'm gonna say from 0 to root n, right? Then the second would have elements from root n to root n minus 1, right? So let's just number them properly. This is the first one. Let's erase this. Yeah. This is the first. Yeah. This is the first one. This is the second one. Similarly, we'll have a third one that would go from root 2 to 3 root n minus 1. Sorry, this is 2 root n. I hope you get it right. And so on and so forth. And yes, obviously, it's not required that my n would be a perfect square. So it could be the case that the like the last box starts at some n, so it could start at some x into root n, right? Obviously I know the value of x, but let's just say it starts at x into root n and it ends at a number, say y, and it's not required that your y is maybe like z root n minus 1, right? It could be anything. For example, let's say your n was maybe like 10, so your root n becomes what's like a root of 10 is 3 point something, so we'll take a 3, or we can take a seal that would give us a 4, right? So let's take the value as 4. So over here the first array would start at 0, would go to 4 minus 1, that is 3. The second would start at 4, would go to 4 into 2 minus 1, that is 7, and the third would start at 8 but would only go to 10, not to 11, right? So over here this has 4 elements, this has 4 elements, but this has only 2 elements, right? So this is something, okay, sorry, yeah, 0 to 3, 4 to 7, 8 to 10, this is only 11 elements. So yeah, your n was 10, then this is gonna go till 9 and it's gonna have only 2 elements. Yeah, perfect. So see over here, all the buckets except the last one are having root n elements, and the last one can have any elements that would be bounded by root n. So it would have definitely like the maximum number of elements in the last bucket would is definitely root n, but it can be anywhere between 1 to root n. Up to this point, is everything clear? Cool enough. If you guys feel any difficulty or if anything is not clear, just let me know. I'll repeat that again. Cool. Let's proceed ahead. So how can I use this information? So this entire construction is very easy to do. I can do it in a simple for loop. So I can say that, okay, I'm gonna go from I is equal to 0 till I is less than n, right? I plus plus, not I plus plus, but because I want to traverse across buckets. So the size of a bucket is, let's say length is root n plus 1, right? Or you can say ceil of root n, whatever, like whichever way you're gonna write it. And then you can say I plus equal to length, right? And inside of it, the size of each bucket, right? The size of each bucket is also a length. So you can say for int j equal to 0 and j is less than length, but the size of the last bucket is not length, right? It could be less than that, or you can say I plus j. Okay, or you can say over here, let me just move this over here and take a different pencil. Okay, till the time j is less than minimum of what? So either I'll have to go till length, right? That could be the size, or the size could be, considering the last bucket, the size could be less, but how much less could it be? Let's figure that part later on, right? For now, I'm considering it could be some value, but I don't know about that, right? J plus plus, and then let's initialize a variable over here to 0, and inside the loop, we can say that the sum plus equal to whatever value I was having. I'm assuming that my values are stored in an array ARR, array of I plus j, right? And after that, over here, so in this loop, in this entire loop, your values got added, and after this you'll say that, okay, I am having a sum now, and the sum belongs to a array, right? To an array which has a position I divided by length, right? So how do we store that? So we can say that, okay, we have some array that is square root sum, right? The I divided by length element of it would be sum. Is this part clear? I do have a code for this. I can directly show you that, but is this part clear or any doubts in this? All right, sounds good. Okay, just let's have a look at it. So over here, what I'm doing is that we have a vector that is square root sums, right? I've defined a simple array of size 16, right? Let's move it. Okay, sorry. Let's move it above. Cool. And then I say, what is the length? The length of, this is the length of each bucket, right? So it's square root n plus 1. I had to take a ceil operation, but could be a floating point number and could suffer floating point precision. So since I'm not going to do that, I'm just adding a 1 over here. And then we have to populate this particular square root sums array, right? So I'm starting from sum. I'm saying that the current element is 0, right? And I'll go up to n. And every time I'm working for the length number of elements, right? So each time I'm gonna add length to I, and my loop is gonna start at j. It's gonna be minimum of n minus I comma length, right? Because it has to be minimum than length. That's known because each of the buckets we had described can contain at most length elements, right? At most len elements, you can say. But the last bucket would not have the capacity to hold that much, right? The last bucket could either be small, or it could be as big as others, but it could be either small as well, right? So that's why I'm doing a n minus I. This is specifically for the last bucket. Adding all the values to sum, right? And then pushing this into square root sums. Other way of doing it could be that you could have said that, okay, this would have a size length, right? And over here you could have said that, okay, of length is equal to sum. This could be another way of doing it, but both the way would actually yield the same result, so I'm not gonna do that. This looks good enough to me, and then I'm gonna say, okay, I just erase that. So okay, cool. Now comes the part, what would happen when I want to query it, right? So let's move back to the pad. Okay, okay, so when I want to query it, the query could be like, this is the array that we already know, right? So this is 0, 1, 2, 3, 4, 5, 6, so on, and to n. And then I say that, okay, give me the sum from 3 to maybe like 7, right? Or 3 to n, anything, or just say L to R. So what you'll do? So let's say our L was maybe like 2. So you'll start over here. You'll firstly check that whether this particular point is the starting of a bucket or not. And how do we check if it's the starting of a bucket or not? The simple fact is that if your I is completely divisible by length, right? If it's completely divisible, then definitely it's the starting, because if you remember, the starting points are always divisible by root n, right? So this is divisible, this is divisible, this is divisible. So these all are exactly divisible by root n. So if the starting index is completely divisible by length, that means it's the starting of an entire block, right? So I can say that, okay, I'm gonna start my I is equal to L, and we are gonna definitely go till R, right? But now what? Should I directly consider this to be a starting of a bucket or not? So for that, I can simply check that if my I is completely divisible by length, then it is the starting of a bucket. But that really doesn't suffice, right? Because let's say this was starting at 4 and ending at 7. But it could be the case that I'm just asking for the sum from 4 to 6, right? In that case, you can't just give me the entire sum, right? So you'll also have to make a check that whether the end index, it if that itself is smaller than the end of this particular bucket, then you won't be including that, right? So a simple way to check it could be, if your I plus length minus 1, right, it should be greater than or equal to R. If this is this holds, right? If this, okay, not greater but less than, yeah. If this holds, only in that case this entire thing lies within the entire range I'm querying for. If this happens, then I can say that, okay, I already know the values. So let's say this is our sum that we are calculating. So I can say that, okay, this entire pre-calculated value can actually be used. So I was having the values in square root sum. I'll directly use this particular value, right? So I'll say, okay, I know that you already have calculated, give me this. And now I've already calculated from this point till this point. So I'll add some value for this, right? So I'll say that, okay, I've already calculated this much. So let's add, like, I've already calculated for these many indices. Let's add all of those, right? So I'm gonna add all of those. And at this point, what essentially has happened is, in a single operation, right? In a single operation or order of one operation, I calculated the values for root n elements. And that's how I'm gonna reduce my time complexity. Because continuing the same operation, if let's say there were maybe like X amount of buckets, right? So this had root n elements, this had root n, this had root n, and let's say there was such X amount of buckets for which this if was applicable, right? Okay, that crashed. Won't expect that from Apple, but never mind. Okay, so let's say this had root n, this had root n, everything had root n, and there were total of X amount of such buckets, right? So in total, I just spent order of X computes on this, but I was able to calculate the value of order of X root n elements. So you definitely see the reduction in the total computation over here, and hence this speeds up the things, right? But wait, uh, why is it even willful? I could have just used the prefix sum, right? And could have done prefix of press of R minus press of L. I hope you know the very basics. So yeah, I could have done this and got my answer. So why is this even helpful? It's helpful because the second kind of update, that is update a index. we can't do this efficiently with this particular approach. So firstly, let's look at the way we try to calculate the sum, and then we'll go over here. So now I've taken this simple queries. I'm populating pairs because it's essentially just a left index and a right index. I'm going to take that from the user, and obviously going to decrease one because it's zero base indexing, and the values I've given is in one base. And then I'm going to initialize the sum equal to 0, right? And over here, I'm going to say that if it's a starting point of a particular bucket and the entire array, right, the entire array is a part of the query I want, so it's going to end at I plus len minus 1. If it's less than equal to r, in that case I'll add the pre-computed answer that was stored in square root sums to my answer, right? And I'm going to increment my I. Else I have to calculate the singular values. Now when would this else compute, right? So else would compute in two scenarios. If I is not the beginning of the array of the bucket, or the second could be it's the last bucket, and our result doesn't require the complete bucket, right? In these two scenarios, this else would be computed, and for all other scenarios this if would be computed. Now it's kind of obvious, but still if you want to check, the else loop would not be executed more than root n times, right? Because this else loop can only be executed at the very first. So if we go back over here, then the else loop can only be executed. So let's say these are the buckets, right? And this was starting at 0 going till 4, then from 0 till 3, then 4 to 8, 4 to 7, then 8 to 11, then 12 to, let's say, like 15, right? And let's say I asked you that, okay, give me the sum from 2 to maybe like 9, right? So essentially you're going to start over here. So at the very beginning, you're not starting at the beginning of a bucket. So for these many elements, you're going to perform that else operation, that is checking for individual elements. But as soon as you reach over here, right, for this entire bucket, you're going to calculate the value in a single operation, right? So that if statement would be applicable. And as soon as you reach here, now you'll say that, okay, I'm standing at the starting of a bucket, but the entire bucket is not required for my answer. So I'm going to use the else statement, right? So again, for this particular part, you're going to use the else statement, right? So even in the worst case scenarios, uh, at max you'll only have to use it two times, right? Or for two buckets. And even like the buckets have a maximum capacity of root n. Again, someone has his mic on, but cool. Okay, so again, the buckets have a capacity of root n. So at max, it's going to take you 2 into root n elements, right? Or 2 into root n times you're going to use the else statements. And let's say we use the if statement x number of times, right? So the overall complexity would be x plus 2 into root n. But what is x? X is bounded by the number of buckets you are having, right? And the number of buckets you are having is also root n. So essentially it's just root n plus 2 root n, or you can say in asymptotic terms, it's order of root n. And that's how and that's how sum also works over here. Now let's look at, sorry, I just forgot to mute my, no issues, cool. But are there any doubts till now? Is everything clear? Because I haven't heard any single doubt up till this point. All right, cool guys. Let's move to the update operation. Cool. So let's just verify the answers first. For example, we're getting 49, 177, 60, 206, 178 for these particular values. Let's just print the values that we should get if we use accumulate function. Now accumulate is a way of calculating the values using the STL functions. So I'm going to say that, okay, I'm going to start at the beginning and add L to it from the Lth index till the rth index. Right. If these two values are same, then I'll know that my answers are being calculated perfectly. And okay, I forgot to give it a 0. It's fine. Okay, so you can see that the values are same, hence our things like the algorithm is working properly. But wait, now what would happen if I say that okay, you have another type of queries, so you'll say give me two index, like you will give me an index, and you'll say that its values has to be updated to some new val, let's say. Right. Then what would I do? I would be stuck, right? Because now I don't know what to do. But it's actually not a problem. So I can say that okay, if you give me an index, let's say index is 10, right? And the value you want me to change is 123. Just giving a big enough value, right? So what I'll do is I'll firstly check which bucket it belongs to. Now, how do I check which bucket it belongs to? The simple thing is it bucket ID would actually be uh, the index divided by the entire length, or the length, okay, length of a bucket. Right. Now by default, like this might not be perfectly divisible, but C++ by default does a floor operation, so we are good over here, right? And then we'll say that okay, I do have the index of the bucket. I want the value to be updated at. Now there could be two ways of doing it. I could either calculate that okay, the initial value was this, the final value is this, and this is the difference, right? And let me just add the difference to the bucket. Or the second way could be that I could calculate it for the entire bucket, the updated value. You can perform any one of this, but the second, like the second approach or the more brute force approach, could be beneficial in cases wherein maybe like you have to calculate the max or the min, because the first approach won't work in that case, right? So what I can say is that I'm gonna start at an index that is, let's say I is equal to bucket ID, right? Okay, so initially I'm saying that I'm at the bucket ID bucket, right? Now what is the index of like starting index of this bucket? It can be updated by multiplying by length, because if you remember, then over, okay, where was it? Yeah, over here you can see that, okay, yeah. So the starting element is always root n, right? So this is the zeroth bucket. Its starting element is 0. This is the first bucket. Its starting element is 1 into root n. That is root n. This is the second bucket, right? Its starting element is 2 into root n. That is 2 root n. Hence, I'm saying that the starting element would be the bucket ID into length, right? And till what point I want to go? So I want to go till minimum of n comma bucket. The next bucket would start at bucket ID plus 1, right? Into whatever length I have, right? And I plus plus. And I can say let's save the values in some value and call it new sum, right? Also, before doing any of this, I have to update the value itself, right? So let's update the value of idx to, okay, to the val, right? And now I can say that my new sum plus equal to v of I, right? And once I have the value stored in new sum, what I can do is I can just update square root sums. Now how do I do it? I already know the index for this. So I'll say, okay, I know the index. So square root sums and bucket ID equal to new sum. That's pretty much it. That's pretty much all you need to do over here. Any doubts on this? Okay, cool enough. So if there are no doubts, that's pretty much that's pretty much square root decomposition for you. This is not a hard concept, but definitely serves as a basis for Moore's algorithm. And on top of that, it's pretty much convenient to utilize this rather than coding up a segment tree in time complexity permits. Just to have a recap, the segment tree definitely provides you with a better time complexity of order of log n for each operation. That could be a update operation, update as well as query operations can be done in order of log n. However, in case of square root decomposition, both the update and the query operation would take order of root n, and it's trivial that order of log n is less than order of root n. So yes, segment tree is definitely faster, but if you have implemented a segment tree, you know that it's far more complicated. I'll not say it's hard, but it's bigger than that and would definitely take more time to code it up if you're not dependent on templates. So over there, this could be helpful. That is number one point. The second is it definitely serves as a basis for Moore's algorithm. So understanding this in detail would definitely help you for several problems that can only be solved by Moore's. If you want to have some more context on which problems can only be solved by Moore's and not by lazy segmentary or any other DS for that matter, you can have a look at the blog Ketan shared. So I'll definitely recommend you guys to have a look at this. This should probably help. Cool guys. So yeah, that's pretty much it for the session. Any doubts for now? And someone is typing. Let's wait.